bar of length 3 meter at the temperature of 20 degrees centigrade is heated up to 100 degrees centigrade and its length is increased by delta L. So if the coefficient of linear expansion of the aluminum is 3.31 times 10 raised to minus 5 per Kelvin, then what is the ratio of change in length to the original length in percentage? So to do this, first we use the concept of the linear expansion, which says that change in length is equals to the original length times the coefficient of linear expansion alpha times the change in temperature. So then if I divide this equation by L naught to both sides, then I can get directly delta L over L naught is equals to alpha times delta T. But delta T is equals to delta T means the T final minus T initial, which is equals to 120 degrees centigrade minus 20 degrees centigrade is 100 degrees centigrade. So this means that change in temperature in Kelvin is also equal to change in temperature in degrees centigrade. So I can use as a Kelvin or as a degree centigrade. So then change in length with respect to the original length L naught is equals to alpha is 3.31 times 10 raised to minus 5 per Kelvin times change in temperature is 100 Kelvin or 100 degrees centigrade. So I can cancel Kelvin here and we have left with 100 means simply it is 10 raised to 2. This is 3.31 times 10 raised to minus 5 times 10 raised to 2. So minus 5 plus 2 is minus 3. Exactly we get that 3.31 times 10 raised to minus 3 is left. But this is not the final answer since the equation requires in percentage the change in length with respect to original length ratio in percentage is equals to the value we get 3.31 times 10 raised to minus 3 times 100%. So this is equals to directly 0.0331%. So the correct answer is on alternative D. A very large tank is filled with oil and the density of the oil is 800 kg per meter cube and the atmospheric pressure is given as 1.01 times 10 raised to 5 Pascal and the absolute pressure at the bottom of the container is 1.81 times 10 raised to 5 Pascal and the gravity is now 10 meters per second square. And then what is the depth of this oil? So to find this, we use the concept of the fluid static. That means that the absolute pressure at any point or the absolute pressures at the any depth or the static pressures of the fluid at the any columns of the container is given by the absolute pressure is equals to the atmospheric pressure plus the pressure due to the columns of the fluid, which is given by rho G times A. Then from this equation we can directly find H. That means H is equals to P absolute minus P atmosphere divided by density times G. Then directly when we substitute this value on, we get that it is 1.81 times 10 raised to 5 Pascal minus 1.01 times 10 raised to 5 Pascal divided by 800 kg per meter cube times 10 meter per second square. This is directly equal to, if we subtract this number, we get 0.8 times 10 raised to 5 Pascal divided by, this is 8,000, or simply we can say it is 8 times 10 raised to 3 kilogram per meter cube times meter per second square is directly given by Newton per meter cube. So if we rearrange this number, then this number becomes, the numerator is 8 times 10 raised to 4 Pascal divided by 8 times 10 raised to 3 Newton per meter cube. But we know that Pascal is equals to Newton per meter square. If I divide Pascal to Newton per meter square, this means that Newton per meter square times meter cube per Newton. So Newton cancel with the Newton and meter square cancel meter square and only 1 meter is left. So H is measured in meter. So if I divide this number directly, 8 divided by 8 is 1 times 10 raised to 4 minus 3, which is directly 1 meter is left. This means that H is equals to 10 meters. So the depth of the oil is 10 meters and the correct answer is on alternative C. container resting on the floor of an elevator containing an incomprehensible fluid of density rho. When the elevator has an upward acceleration A, that means the elevator is moving upward or it's accelerating upward. So then what will be the pressure difference between the 2 points in the fluid separated by a vertical distance? Then what will be the pressure differences between these 2 points, that is the upper and the lower or the bottom of the container? So to find this, we use the equations of the static pressures. That means the difference in pressure between any 2 points in the fluid is given by the density of the fluid times the effective acceleration times the difference in height between 2 points. So this means that the effective acceleration is directly given by since the elevator which containing the fluid is accelerating upward, the effective accelerations of or the total accelerations of the fluid is given by the accelerations of the elevator plus the acceleration due to gravity g. Then directly if I substitute in the value, the difference in pressure between 2 points is density times effective accelerations times change in height, the height differences between 2 points. So this is density times the effective acceleration is acceleration of the elevator plus the acceleration due to gravity and delta h. So just we can conclude that the difference in pressure is the density times the sum of the acceleration of the elevator and the acceleration due to gravity times the difference in height of the 2 points. So the correct answer is on alternative B. Water flows through a fire hose of diameter, that is the larger diameter, which is capital D 6.35 centimeter at a rate of 0.012 meter cube per second. Then what is the speed with which the water exceeds the nozzle? That means the nozzle, if this is the nozzle, that is the outlet, and the water is entering here with a flow rate of Q this much, then what will be the speed? So from the flow rate equation, from the volume flow rate, that means from the fluid dynamics, we know that the volume flow rate Q is equals to, which is the volume of the water or the fluid flowing per time, but the flow rate of the in is equals to always the flow rate of the out. That means the rate at which the water is entering the inlet is equals to the volume of the rate of flow of the water that is coming out from the outlet is out to the nozzle. So this means that the flow rate is given the in and amount of the water entering and amount of the water coming out in a second are equal. So this much meter cube per second. Then what will be the speed? So as we know that as the diameter of the outlet is decreases, the speed at which the fluid come out from the outlet is increases. So to maintain the flow rate, so the speed must be increased at the outlet. So we are going to find that speed. Then we know that the area of the inlet times the speed of the in is equals to area, cross-sectional area of the outlet times the speed at which the water comes out. So we know that this is equals to directly the volume flow rate Q. So to find the velocity outlet from the nozzle, so V outlet is equals to the volume flow rate divided by the area of the outlet. So directly if I substitute the number, this become 0.012 meter cube per second divided by area of the outlet. Means since the outlet cross-sectional area is the circular form, I can write that the area is pi r square, that means pi diameter square divided by 4. So if I rearrange this equation, it becomes 0.012 meter cube per second divided by pi times 2.2 times 10 raised to minus 2 meter the whole square, since the diameter is 2.2 centimeter, that is 2.2 times 10 raised to minus 2 meter multiplied by 4. So if you do these calculations and it becomes, so if you multiply this number all together, because the flow rate is known, pi is constant number, this is the diameter of the outlet, and I multiplied by 4 because instead of dividing the diameter by 2 and square it, so since the radius is diameter over 2, radius square means diameter square divided by 4, then the final answer becomes 31. V outlet is equals to 31 meter per second. So the correct answer is on alternative C. which one of the following is correct statements about the pressure under the fluids, or the pressure due to the columns of the fluid? So we know that the pressures due to the column of the fluid is given by pressure is equals to density of the fluid, acceleration due to gravity, and the depth of that fluid multiplied together. So A says that it depends on the volume of the fluid. So we cannot see volume here, so this is immediately false, it's not correct. B, it depends on the density of the fluid. Yes, it depends on the density of the fluid here, so this statement is correct. C, depends on the shape of the container, so it do not depend on the shape of the container, so this is completely false. And independent of the depth of the fluid, it's not independent, it depends on the depth of the fluid, which is H. So the correct answer concerning the pressure under the fluid is on alternative B.